All right, today we're working on our Unit 3 Day 5 lesson. I'm going to make this one a little bit shorter. I'm only going to do about half of the problems. So if you need more help with this, come in and I will help you. Today we're going to be working with special patterns. So remember the difference of squares pattern. You've been doing this one for a while. If we have something like x squared minus 9, these are both perfect squares, so we can factor it pretty easily as x plus 3 times x minus 3. Well, what if what we have instead is an x squared plus 9? I would like to argue that the way that you can factor this is an x plus a 3i and an x minus 3i. So it looks very much the same. The only difference is that it has the i's, this imaginary part here. So let's see if that works. We're going to test it out to see if it works by simply taking these two factors and multiplying them and seeing if it actually does multiply to give us x squared plus 9. So if we have an x plus 3i and an x minus 3i, well, if we want to multiply this, it would be an x squared, and distribute the x to the negative 3i, that's a negative 3i x. And we also need to distribute the 3i over to the x. That's a positive 3ix. And a 3i times a negative 3i is a negative 9i to the second power. We have an I times an I, so that's I squared. So we've now expanded that. Right here in the middle, we have a negative 3ix and a positive 3ix. That adds up to 0. So what we're left with is just the x squared minus 9i squared. Those ones are gone. Well, I squared, it happens that I know that I squared is equal to negative 1. So this is the same as an x squared minus 9 times negative 1, and that is the same as an x squared plus 9. So in fact, our two factors do multiply to give us x squared plus 9. So this pattern that I'm using now, instead of being called the difference of squares, difference is subtraction, this is called the sum of squares. If we have a squared plus b squared, so we only have two terms, two terms, and they're both perfect squares and they're being added, we can factor it as an a plus bi and an a minus bi. So let's practice a couple of those. X squared plus 100 equals 0. This is a perfect square and this is a perfect square, so we can factor that as it's a sum of squares. In the first position, we'll have an x on both factors, and it would be a 10i and a negative 10i, and that's equal to 0. So if we want to solve for x, because this equation is equal to 0, we're interested in knowing what x equals. Well, from this first term, we find out that x is negative 10i. And from the second factor, if we solve x minus 10i equals 0, we get that x is positive 10i. So here are two solutions. And yes, if you like, it is fine to write it as plus or minus 10i. All right, so one more of these. If I want to solve this 9x squared plus 4 is equal to 0, if I want to use factoring as my method of solving it, well, 9x squared is a perfect square of 3x, so we'll have a 3x and a 3x. And 4 is the perfect square of 2 plus 2 and minus 2, but this is a plus that tells me that I need to include i's. So 3x plus 2i and 3x minus 2i is equal to 0. So if I continue solving, if I set each of these factors equal to 0, in this case we would subtract the 2i and divide by 3. And for the other factor we would add the 2i and divide by 3. So if you want, you could write it as plus or minus 2i all over 3. So as you're looking at these that have perfect squares, just be really careful to notice if it's plus or if it's minus. If it's a plus b squared, you're going to have imaginary parts, and if it's a difference of squares, you'll just have what we're normally used to without the i's in it. So just pay really close attention to the signs right here. Okay, the next pattern we're going to talk about is the cubic patterns. We have a difference of cubes. Difference just means that you're subtracting, or a sum of cubes. So before we go straight into the pattern, I want to talk about recognizing perfect cubes. So here are a list of possibilities. We're going to figure out which of these are perfect cubes. So if we start right here with 64y to the third, if I'm thinking about what would I raise to a third power to give me that as an answer, oh, my 3 is like not working out there. There we go. Well, to get the coefficient 64, we would raise 4 to the third power, and then we also have a y that's being raised to the third power. So 64y to the third is the perfect cube of 4y. Let's go over here to 27. If I'm thinking about what would I raise to the third power to get that, it is a perfect cube. It's a perfect cube of 3x. Let's look at 30z. So maybe you're thinking, well, the z is just going to be a z here, z to the third power, but there is no number that I could put here that we could raise to the third power and get 30. So this is not a perfect square, or sorry, a perfect cube. Let's go down here to the 216 now. 216, I happen to know, is 6 to the third power. And if we're thinking about what variable we might raise to a third power to get x to the 6th, that would be x squared. In this case, you would multiply these two powers to get the 6th power on that x. And there's a few more here. Let's see. 100x to the third power. 100 is a perfect square, not a perfect cube. 9x to the third power is a perfect square. 9 is a perfect square, not a perfect cube. So that's a weird combination that doesn't work to make a perfect cube. Up in the corner here, 8y to the 6th. That would be 2 raised, to the second power. So 2 to the third power will give me 8, and y, whoops, oh my goodness, I can write. Y to the second power, if that's all raised to the third power, that will give me y to the 6th power. So as we're using the sum and difference patterns with cubes, we have to become really good at spotting these perfect cubes. 125, yes, that is a perfect cube. It is the cube of 5m. X to the third, y to the third is also a perfect cube. It's the perfect cube of xy. And the last one over here, it is a perfect cube. It is the perfect cube of 2x to the third, and then that would be raised to the third power to give us 8x to the 9th. Anyway, point of this is just to start really recognizing when you see a perfect cube number or term. So here are the two patterns. If we have a to the third minus b to the third, that factors as an a minus b times an a squared plus ab plus b squared. And the sum of cubes is very similar. A to the third plus b to the third is a plus b times a squared minus ab plus b squared. What you maybe might notice about these formulas is that they're very similar in terms of what letters you see. Both have an A here and here and here. They both have B's in these positions that are exactly the same. With the power 2, those power 2's are the same as well. For these two patterns, The major difference that you might notice is actually just the signs. If our original problem has a negative in it and we want to factor that, when we factor, it will have these signs. The factor of the binomial is negative, and then these other two are both positive. If your original problem that you're trying to factor is positive, it will start with the positive here in this term, and then it will be negative and positive. One way to help you remember that, which way the which way the signs are, is a little memory tool, SOAP. Whatever you start with, this one's negative. The first one is the same, which in this case is negative. The second one is opposite. Opposite. Wow. In this case, that would be positive. And then the last one is always positive. So SOAP, SOAP. That works with both patterns. This one starts with positive. So the first one is the same as we started with. The second one is the opposite of that. And the last one is always positive. So SOAP can maybe help you make those signs the right way. So let's try to factor one now. X squared minus 8. This is a difference of cube. They're being subtracted. A minus B. So here's the pattern that we're going to use. And what we need to think about is what our A and B are. Well, we have an x to the third minus 8 is the same as 2 to the third. So you might, if I write it that way, you might be able to see more easily that the A is equal to x and the B is equal to 2. B is not 8. That is probably the single most common error people make. B is whatever would raise to the third power to give me 8 as the answer. So if we put that into our formula, it tells us that this factors as an x minus 2. So I put the A and B in. And now I need to square A, so that's an x squared. For the next term, I want to take the A and multiply it by B. X times 2 we normally would write as a 2x. And the last term is B raised to the second power. Well, 2 to the second power is 4. And that is our complete factorization. So x to the third minus 8 is the same as x minus 2 times x squared plus 2x plus 4. Now I think it's worth mentioning that when you use this pattern, this quadratic right here cannot be factored more. It's called a prime quadratic. You can't factor it anymore. There are no factors of 4 that add up to 2. So that is our final answer. Okay, I'm going to skip a couple of these practice problems so that the video is not forever long. All right, so now this one, pretty similar, 27x to the third plus 1. You should recognize 27x to the third as a perfect cube, and 1 is also a perfect cube. It's 1 to the third power. So let's see, let me write up my pattern. A to the third this time is plus. So our pattern has the same sign, then it has the opposite sign, and the last one is always positive. So what we have is 27x cubed plus 1. So our A is like a 3x that's being raised to the third power, and B is 1. So this is A, and this is B. And again, I came up with A because I thought, what would I raise to the third power to get 27x to the third? So let's substitute those values into our pattern. 3x plus 1 is our A plus B. And now I need to have A That's a 3x, and I need to square it. So please note that the 3 is part of a, and so it also gets raised to the second power. This will be a 9x squared. And now I'm subtracting, and I want to take a and multiply it by b. Whoops, that's a 3x times a 1, so just 3x. And then finally, our last term is to take our b value and square it. Well, 1 squared is 1. So this is our complete factorization of 27x to the third plus 1. Okay, to example 3 now, we have something that is a little more complicated. It's still a difference of cubes. 125 is a perfect cube of 5. 8 is a perfect cube of 2. So I'm going to write my pattern out here. A to the third minus b to the third. This one is a difference. So here's the pattern that we will use. So if I'm thinking about a, well, in that position in my little formula at the top there, it's 125 x to the third. So if I'm thinking about what is raised to the third power to give me that, it is a 5x. And for b, if we're thinking about what we would raise to the third power to give us 8y, it's 2y. So our a is 5x and our b is 2y. So let's put that into our formula. 5x for a, subtract b. Move this over a little. And now is maybe a little bit more tricky. I want to take my a, that's a 5x, and raise it to the second power. So 25x squared. And then the next part is a times, which is 5x, times b, which is 2y. So we have a 5x times a 2y. That would be a 10xy. And in the last position, we want to take our b value and square it. When we do that, 2y, if that is all raised to the second power, that's a 4y squared. So maybe a little more complicated looking with those two variables, but it's the same pattern. Figure out what the heck a and b are, and then you can just put them into the formula somewhat carefully. So there's our factorization. Okay, skipping this. All right, so now we get to the real fun part, solving. If we have an equation like this, x to the third minus 8 equals 0, we want to solve for x. So we're going to use as our method of solving today, factoring. So we have to think about what our a value and our b value are. Well, in this case, a is x, and b, we're thinking about what number would give us 8 if we raise it to the third power, so our b is 2. So if we put those into the equation, we will have x minus 2, that's a minus b. Now we want to square our a value, that's an x squared. We're going to add together a times b, so that's a 2 times x. And finally comes b to the second power, which would be 2 to the second power, which is 4. So we have a product here. We have x minus 2 times x squared plus 2x plus 4. And that product is equal to 0. So the zero product property tells me that one of those two things must be 0 or both. Our first solution comes from the factor x minus 2 equals 0, and we get the solution x equals 2. Well, remember, this is a cubic equation. We should be expecting 3 answers, so we should be able to find 2 more. Those come from when x squared plus 2x plus 4 is equal to 0. Now, a minute ago, I said this is not factorable, and it is not. There are no factors of 4 that add up to 2. So if we have a quadratic that we want to solve and it is not, and it is not factorable, we have to use the quadratic formula. Oops, I lost my pen. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Well, in this case, if we use this quadratic here, it's a 1x squared plus 2x plus 4x is equal to negative 2 plus or minus the square root of 2 squared minus 4 times a times c, and that's all divided by 2 times our a value of 1. So if we work on simplifying that a bit, we have negative 2 plus or minus the square root of, and if we figure out what's inside the square root here, it is negative 12. You could type that in your calculator to get it. So we're almost finished. We just need to finish simplifying this radical expression to see if we can simplify it a bit more. Well, negative 2 plus or minus the square root of negative 12 is the same as the square root of negative 1 times 4 times 3. The negative 1 gives us an I when we take the square root of it. The 4 gives us a 2, and the root 3 we can't do much with. So this is a 2I root 3. And then we still have that all being divided by 2. So you might notice that we have a factor of 2 in all of those positions, so we can reduce that. And so we end up with x is equal to negative 1 plus or minus I root 3. And it's really just, in this case, divided by 1 now because we reduced that 2. So here are our other 2 solutions for a total of 3 solutions. All right, I'm not going to go through this whole problem. I just want to show you the beginning. If we want to solve this degree 4 quartic polynomial, we might want to first have it equal to 0 by adding that 125 to both sides of the equation, 125x, I should say. So now it may not necessarily look like a difference of squares or a sum of squares or a difference of cubes or a sum of cubes right now, but if you pause and remember that you should always look for a common factor, you might notice that both of these have a factor of x. We could factor that out. Now that we have that common factor factored out, this looks much more like a pattern with cubics. We've got a sum here, and our a is going to be a 3x, and our b is going to be 5. So it'd be a 3x plus 5, same sign. If we square that a value, we get a 9x squared minus, we times a and b together to get 15x, and then finally b squared. And that's equal to 0. So 2 of the solutions are right here, x equals 0 and x equals negative 3/5. The other 2 solutions are here. I'm not going to go through the quadratic formula for this video, but if you were solving this problem, you would continue that. And so that is it. Those 3 new patterns, we're just adding to our group of patterns that we can use now. Next time, we will be having our review of the unit, and then we will have our test. For A day, the test is Friday. For B day, it's Monday. And if you need some help before the test, please come in as soon as possible, before school or at lunch or after school, any day except for Thursdays. Thanks.